Hello, everyone. In this lecture, we want to implement our previous scenario with a real implementation of Groth16 in Python. And then we will discuss another scenario and overview the implementation, the practical implementation. Okay, so let's review first the scenario. We had auction that multiple company apply for a project, and then there were some referees that grade the application and send the grade to auction man that play the role of prover. So then in the decision day, the prover computes the final grade of the application and then send the uh, final grade with a proof to the audience. And we mentioned that to design a ZKP scenario when the auction man be able to generate a proof that the final computation, the final grade is correct, we need a trusted authority that run a key generation algorithm, decide elliptic curve, and then decide a prime value, and then generate the field, and then publish the SRS values. And later, the prover, which is the auction man here, um, generate a proof, which was the combination of commit of different polynomials, right, to the verifier. And then verifier run pairing algorithm to see that if the pairing of commit values are equal in two sides of the equation or not in test version 4, which was the final test, right? Okay, so you remember that for our manual computation, we use two group, right? Group G1 and group G2. And both the group G1, both of them are generated from the elliptic curve y to the power of 2 equals to x to the power of 3 plus x plus 9. So the first group generated by the final field f sub 101, and the second group was generated over the field, the extended field, right? So you remember that all the SRS values, they were the points from group G1 or some element from group G2, right? Every values they are generated, they are included in this group. And also the commit values. So yeah, so also these values also, they are elements of group G1 and these values similarly, right? So, and you remember that the commit values, they are also elements from the group G1 and group G2. For instance, this commit, since it is generated by the values from G1, so the final value for this part would be an element from this group, right? Or for this one, which is a commit over G2, so the result would be an element from this group, right? Uh, and then at the pairing, at the verification side, so two values from group G1 and G2 are given, and then the final group, the group target is also a group generated by the extension field. Okay, so we have used a small value for the prime, which was 101, to make the computation, the manual computation, easy to understand and to compute, right? But what happened in practice? So in practice, we do not use so a small value for prime. And also the elliptic curve polynomial might be different uh, to provide the property of pairing friendly curve, right? We discussed in the lecture of pairing that not all curve are proper to compute pairing. So here we have some standard a pairing friendly curve like BN128, which the elliptic curve, the formula is this one. So here we see that the formula would be different from our decided formula, and also the value, the prime value, it's so big, right? So our chosen value was 101, but the practical value in this standard curve is so big. So we cannot use this big value and then do the computation of the uh, key generation algorithm, or computing the SRS, or computing the commits by manual, but all the process and the method would be very similar to the scenario that we computed manually. So now we want to just overview a Python code that implement this scenario, but with a practical and a standard elliptic curve. Okay, to do this, we switch to our website, and in the Groth16 tab and Groth16 here, we have different option. And the first one is ZK auction, which is a Python code that implements the discussed scenario. So the ZK auction scenario here, it is implemented here. Okay, let's review what happened in a practical scenario, not a simple and manual scenario. First, we need to install the libraries. So these libraries do the computation for practical and standard curve, like BN128, the curve that we discussed before. So these libraries do the addition for the points for scalar multiplication or pairing, and those different functions that we need. Okay, so the first step, like our previous discussion, is to converting the puzzle into a circuit using the constraint system, right? So you can write the constraint system like very similar to the form that we already have written, right? So the constraint system would not be changed. And also the circuit definitely would not be changed. But here, instead, instead of prime 101, we will use the standard value for the prime, the big value for the prime. And also we enter the value for the x1, x2, and x3, but in form of the final field of the new prime. Okay, after implementing, after running this part, we want to convert the circuit into the matrix. So we have written the new scenario based on the sorry, yeah, this is actually the same like the matrix that we discussed in previous lecture, right? The matrix of XL, XR, and XO. So this means that if scenario is changed, then we need to update this matrix. So we could write the code in a way that the code automatically updates this matrix, but we wanted to do this manually to show you how it works. Okay, so it took time to import these libraries. After converting the circuit into matrix, you remember that we had a naive protocol, right? So the naive protocol, we had the prover had a matrix of W, right? You remember the W matrix was 1, y, x1, x2, x3, and v1, v2, v3 values. And then based on the given values by the prover that he knows, we want to check this test to ensure that if it's correct or not. And then we see that this test is passed. So you remember that the two values already discussed in the previous lecture, and the result is exactly the same like the previous lecture. However, later we discussed that the naive protocol is not secure and is not zero knowledge, is not succinct, blah, blah. And then we discussed some other scenario, and we needed to convert the matrix into polynomial and then use the commit to generate the proof, right? Okay, so let's see here. Okay, this is not implemented yet. Okay, anyway, we can continue. So here we can, now we want to convert the matrix into polynomials, and then we will use the Lagrange formulas as we discussed in previous lecture to convert the matrix into polynomials. Okay, okay, this is not implemented yet because the previous part is not done. Okay, now it is done, and uh, the polynomials are computed now. So we see that the coefficient of the polynomial is so big values, different from the manual example that we discussed in the mm, in the previous lecture, because now we are using a very big and practical prime number. Okay, so now we want to compute the polynomial t of x and h of x. So this part would be done by the prover. And again, we see that the coefficient of these polynomials are big values because we are working in practical field, but the degree similar to previous lecture is the same. So the degree of t of x is 4. Okay. Uh, okay. So now we want to run the fresh test, the test version 1, and this test should be done by the uh, trusted authority, right? To generate the SRS or public parameter. Okay, so we see that the tau value is decided 20. In previous lecture, I think that it was 5. So here it is 20, and then the SRS values are computed here, right? So the SRS over the G1 is this values and these so big values, right? You see, this is just one element from group G1, you see? So this is the X part, and this is the Y part of the element of the point from group G1. Because right now we are forming group G1 and G2 by the so big field, by the big value of the prime value, right? So then we would have billions and billions points in group G1, and uh, maybe trillions of elements in group G2. So this is one element of group G1 and the X part and the value part of uh, this point. So this is the third element, right? The third point, and this is the fourth point uh, of the SRS1. So the other SRS2, if you remember, it was generated by the element from a group G2, right? And you remember that the element of group G2 consists of four parts for each element, like maybe 2 plus 3i and 3 plus 6i, something like that, right? So this means that we have four number for each element. Now, this is the first element, right? So this is the first element. You see, the first element consists of four number because we have four values to define an element in group G2. And all of these values are big values, right? So the first element, and this is the second element in group G2. Maybe, okay, yeah. This is the second element from group G2, and this is the third element in group G2, right? And this is the fourth element in group G2, right? So let's go back to our slides. So here you see that in our slide, the SRS values. So the SRS values in, let me see, yeah. So 1, 2, 3, and 4 SRS 1. And also we had 1, 2, 3, and 4 elements for the SRS number 2, right? And you see that each element in SRS number 2 consists of four number to be defined, right? So this is, for instance, 1, 2, 3, 4. So we see that the number of SRS and the formulas of the SRS is exactly the same. The only difference is that the size of value are big because in our implementation, we are using a standard and big value for prime, right? So SRS, the third SRS also consists of four elements and the values from group G1. Okay, so after the SRS value in test one is generated, so prover will generate the proof. And you remember that the proof in the test one was the commit of polynomial L, commit of polynomial R, and commit of polynomial O plus H, something like that, right? Now we want to ask the prover to generate the proof. And we see that the proof of the uh, uh, polynomial L of x is an element from group G1, right? You remember that the commit of a polynomial was just an element from group G1 or group G2. For polynomial L of x, it was an element from group G1. But for polynomial R of x, it's an element from group G2, right? So that's the reason we have four values to define the commit value, right? And then the commit of O of G also is an element from group G1. Commit of HT is an element from group G2. And then the prover needs to add these two values to each other. An addition of two elements from group G1 again would be an element from group G1, right? You remember this. Okay, now prover will send this value and this value and this value as the proof to the verifier. And the verifier would compute two pairing to see that if they are equal to each other or not. Okay, we see that the pairing of uh, polynomial L and R is this value, right? So this is the pairing of commute of polynomial L of x and R of x. So you remember that the pairing in our computation was an element from group GT, right? And it was, and each element in group GT was uh, just two values to define an element because the group GT was generated by an extension field f sub p to the power of 2. However, we see that one element in group GT here, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? You see 12 elements of or 12 values are used to define an element in group GT. So this means that in practice, in practical implementation, group GT is not extended field p to the power of 2. It's an p to the power of 12, right? So that's the difference. So this means that each element in group GT is in this form, like maybe A plus IB plus JC plus KD, something like that, right? So that's the difference. So we see that now our extension field is in is defined in a higher uh, form of extension. Okay, so the pairing of the right side, again, also an element from group GT, and we see that different parts of these two pairing values are equal to each other, and now the pairing check is passed, right? Good. Now we want to check the second test. So you remember that in second test, the trusted authority need to decide values alpha and beta, and we see that alpha is chosen 2 and beta is chosen 3. And then the trusted authority compute the psi value, and then the SRS, update the SRS value, right? So you remember we had alpha G1 and beta G2 in test number 2. Okay, now again, the prover will generate the commit value, and then the verifier would run pairing and see that the two pairing are equal to each other, and then the test is passed. So in the third algorithm, in the third protocol, the prover, the trusted authority, would generate the uh, the psi value also as the public parameter, right? You remember that in the third, in the protocol version 3, the trusted authority generates the public parts of the psi. And then again, the prover will commit the polynomials and then generates the commit as the proof, and the verifier would run this verification test, right? Commit of LG1 plus alpha G1 and commit of R G2 plus beta G2, the, the verifier will compute the pairing of these two values. And the pairing of these two values, we see that again, this is 1, 2, 3, 4, 5, and then 12 number. We have 12 number to define the result of the pairing. Okay, again, the result of pairing are equal to each other, and then the pairing test is passed. Now the final test, the test version 4, the prover will decide R and S values. So the R value here is 12, and the S value here is 13, and then the prover will update the proof values in combined value of R and S and send to the verifier, and then the verifier would check this test pairing of commit of LG1 plus alpha G1 plus R delta G1 and the second part. So we see that these two values are computed here and they are equal to each other. So then the test is passed, right? Okay, so we saw in this implementation that the method, the protocols, the algorithm, they are completely the same. The only difference was that the values are bigger, and also the target group in computing pairing was in a bigger extension field, right? It was not just two value for each element. 12 value are needed to define each element. Okay, so let's go back to our PowerPoint. Okay, so okay, done. We discussed the implementation, the real implementation of this scenario, the ZK auction. So the prover used the generated SRS values and then generate the real values for the commit, and then verifier check the correctness using the pairing. Okay, so now we want to see that what happened if we work with another scenario. So suppose that we have a DeFi scenario. A protocol needs to evaluate the financial health factor of a user to evaluate that if he should receive a loan or not. So we have designed a simple scenario because we want to get the idea, right? So we assume that there is a formula that computes the health factor of a user using this formula when X1 is the collateral amount of the user, X2 is the requested loan value, and X3 is the credit score of the user. So now we want to compute the health factor of the user without knowing the collateral amount, the requested loan value, and the credit score of the user. So how we can do that? Yeah, using ZKP. So the user can implement an Groth16 algorithm and then generate a proof and send that proof to the server, and then server can check to see that if the Y value is bigger than a specific value or not, and then decide to pay the loan or not. However, the X1, X2, and X3 values for the user is hidden from the server. Okay, now we want to see how we can do that. Uh, First, we need to convert this scenario into a circuit using constraint system, right? So this was the general formula of the function. We can consider it as a puzzle or a function or anything like that. Okay, we want to write this in R1CS standard, which is used in Groth16. So how was the standard? From the previous lecture, we saw that the constraint system in Groth16, it was in this form. Each statement should be written in this form, term 1 and multiplied by term 2 plus term 3. Now we want to write the formula in this form. So first we want to generate x1 to the power of 2 to have this part, right? So we write x1 multiplied by x1 equals to v1, and we have it in our circuit. Then we generate x1 to the power of 2, which is used in this part and this part. And then we generate x3 to the power of 2, which is used in this part. And then we multiply x1 and x2 to have this part as v4, and then multiply v1 and v2 to have v5, and finally, okay, so this is v5, right? So multiply these two parts to each other to have v5, and then add all of these values to each other, and finally reach to the value of y. Okay, now we have written the formula of computing the health factor in an standard form of R1CS, which is used in Groth16, right? Then we need to, if we want to use the Python code that we already discussed, we need to update the SRS part of the code and also the matrix part of the code, right? So we would update the SRS code in this form because we want to write the the constraint system in this form. And also we would update the matrix part of the code in this form. And then the other part would be that completely the same like the ZK auction scenario, converting the matrix into polynomial and then uh, generating the SRS, computing the proof, verifying using pairing, blah, blah. We just need to change the constraint system part of the scenario. Okay, so let's see the scenario in the implementation. So again, we come back to our website, and this is Groth16 part, and this is the ZK circuit scenario. Okay, in the ZK circuit scenario, again, we need to run the standard libraries, and then we see that the circuit is changed here. We need to change the circuit, the constraint system in here, right? So let's see the ZK auction, the constraint system in ZK auction. You see, this is the constraint system in ZK auction, consists of just 4 gates or 4 constraints. So here we have 6 constraints, and our circuit also has 6 gates. So we just updated the constraint part, right? You see, we just update the constraint system part, and also we change the input of the circuit because we assume that the user has different inputs for this circuit. Okay, now we want to, okay, let me see if it's done. Okay, now we want to run this part, and then this part is also changed. The the yeah the matrix pulse also should be changed, right? So this is the matrix part in scenario ZK auction, but the matrix part in um, ZK credit is different, right? The formula of the witness vector also is changed because we have V3, V4, and V5 also in this new circuit, right? So that's the reason the format of W is changed. Okay, so yeah, this was the format of W in ZK auction, and this is the format of W in ZK credit. Yeah, we can update this code in a form that the code automatically update the matrix form and also update the W vector, but we intentionally didn't change this part to do it automatically to rehearse the process and allows you to uh, review how it would be done in practice. Okay, after these values are done, so let me pause the video and I will come back when it's done. Okay, now it is implemented and the matrix are updated and the naive test is also passed. Now we want to convert the new matrix into the polynomials and then compute the polynomial T of x and H of x, and then the prover, the trusted authority will generate the SRS, and it would be definitely very similar to the previous scenario. So here the prover generates the commits, and then the verifier uh, will run the pairing algorithm to verify, and the pairing verification is passed, right? So if you check, you can run the test version 2, 3, and 4, and they would be the same like ZK auction. So we have changed the scenario, and the only part that we changed was this part, right? The constraint system. We update this constraint system, and also we update the matrix. So the matrix would be updated automatically based on the constraint system also. So this means that if you want to run another scenario, the only thing that you need is to update the constraint system part and then the matrix part, and then done. The ZKP system would be implemented. Okay. Okay, so remember this slide from lecture one. We discussed that we have two kinds of ZKP system, custom design and general purpose design. The custom design was like various Baldo or color bar, something like that. But the general purpose, we mentioned that there are some general purpose system like Groth16 that you can use Groth16 to implement any kind of puzzle or function using such a general purpose system, right? You saw that we just changed the constraint system part of the ZK auction scenario, and then we implemented a scenario for ZK credit, right? So if the puzzle is different, like this one, for instance, in this scenario, approver claimed that I know the correct answer for a Sudoku puzzle. So you just need to update the constraint part of the Python code and then the matrix also, and then done. The implementation could be executed, and approver that claimed that I know the correct answer for this Sudoku puzzle can generate the proof and then send the proof to the verifier, blah, blah, something like that, right? So for age verification scenario, we also have the same thing. So you can update the constraint system in a way that evaluates to ensure that if somebody is older than 18 or something like that, and then update the matrix and then done, right? So that's the reason we say this is a general purpose system. You just need to update the constraint system. That's it, right? Okay, thank you. In next lecture, we will overview Circom programming. So Circom programming uh, allows you to write the code, or actually allows you to update the constraint system based on your scenario. Okay, we will discuss what is the difference. Thank you and see you in next lecture.